All right, folks, we're going to do percent yield. This is worksheet 2. These are problems 1 through 4. Look at the next podcast if you want to see the problems on the following page. All right, we're starting with 15.5 grams of ammonium chloride. It's reacting with excess silver nitrate. Two compounds sure sounds like a double replacement reaction to me. In the reaction, we're producing silver chloride. Now, it really sounds like a double replacement reaction. So let's go ahead and write our double replacement reaction to start off, because that's the first thing we have to do. We have ammonium chloride. Ammonium is NH4. Chloride is Cl. It's reacting with excess silver nitrate, AgNO3. And it's producing silver chloride, AgCl, which means the other product is NH4, NO3, ammonium nitrate. All right, so it's asking what's our percent yield. So we're starting with 15.5 grams of ammonium chloride, and we have to figure out, because it tells us how much silver chloride was actually produced in the lab. So what we have to do is figure out how much silver chloride should have been produced. All right, well, to do that, we need to know the mass of ammonium chloride. So let's start with NH4Cl and figure out its molar mass. And if we figure out the molar mass of NH4Cl, it is 53.492 grams per mole. And clearly we have to do the same thing for silver chloride. Silver, of course, is a lot heavier. So we find that to be 143.323 grams per mole. All right, we don't have to worry about limiting reactants because we're told we have excess silver nitrate. So we're going to start over here with ammonium chloride, and we have 15.5 grams of ammonium chloride. And we are trying to get to how many grams of silver chloride that will produce. So I have to get rid of grams of NH4Cl and go to moles of NH4Cl. This is going to be pretty easy because all of our coefficients are 1. The moles of AgCl. We go from moles of AgCl to grams of AgCl. So let's look and see what we have. 1 mole of ammonium chloride. We have figured out that the mass of that is 53.492 grams per mole. And our coefficients we said are all 1. And 1 mole of silver chloride weighs a total of 143.323 grams per mole. So when we actually do this math and come up with how many grams of silver chloride we expect to get, we find that that number is 41.5 grams. Well, we only have 35.5 grams that's produced. So we have to remember that our percent yield is what we actually got over what we expected times 100. So what we actually got was 35.5 grams, and what we thought we were going to get was 41.5 grams. So when we divide that out, we get, we have to multiply that by 100%. Right? Other than that, you're going to get a fraction, excuse me. So your answer here is 85.5%. 85.5%. All right, so that's the first one. Let's go on to a second one. In an experiment, we have potassium chlorate and it's decomposing. Well, potassium chlorate is KClO3. And KCl decomposes into potassium chloride, which is KCl, plus oxygen gas. Well, clearly that's not balanced because we need to have 3 of these and 2 of those to make it 6 oxygens. So that means we have to have 2 KCl's. So we are now balanced. And all we have to do is we have 32.5 grams of potassium chlorate. That's 32.5 grams. And it decomposes into 15.2 grams 15.2 grams of potassium chloride and some oxygen gas. So we're not looking at our oxygen gas. We're simply looking at our potassium chloride. Now, we really have to figure out what we should have gotten. This is what we actually got in the lab when we did the reaction. So we have to figure out what we should have gotten. But to do that, we need to figure out what the molar mass is of KClO3. And the molar mass of KClO3 is 122.548 grams per mole. And the molar mass of KCl, because we need to get that as well, of KCl is 74.551 grams per mole. All right, so let's actually do some math. We start with 32.5 grams of KClO3. We have to convert from potassium chlorate, from grams of potassium chlorate, into moles of potassium chlorate. And from moles of potassium chlorate, we have to go to moles of KCl. And from moles of KCl, we have to go to grams of KCl. All right, well, let's see what numbers we have. We know that 1 mole of KClO3 weighs 122.548. And we have every 2 moles of KClO3 gives us 2 moles of KCl. That's according to our coefficients in the problem. And then what we do is we say, well, 1 mole of KCl, it has a mass of 74.551 grams per mole. So when I actually do the math here and come up with an answer, I come up with 19.8 grams as what we expect to get of KCl. But we didn't get 19.8, we only got 15.2. So our percent yield is equal to our actual, which is 15.2, divided by our expected, which is 19.8. We multiply by 100%, and that gives us a 76.8%. So that is our percent yield. We got 77% of what we expected to get. All right, let's go on to a new one. Nitrogen gas reacts with hydrogen gas. Make ammonia. Nice of them to tell you what ammonia was. It was NH3. You have to remember that both nitrogen and hydrogen are diatomic. They're both Brinkelhoff elements. So to make this thing balanced, we're going to have to put a 2 in front of here. And that means we're going to have to put a 3 in front of our hydrogen. We only have a 1 in front of the nitrogen. All right. We have 15.5 liters of nitrogen gas, and it's making 30 liters of ammonia. And what we have to figure out is how close are we to what we expect to get. So, don't have to do any math to figure out the masses because everything is in liters. So we start with 15.5 liters of N2. We have to get rid of 22.4 liters in 1 mole. And what's our molar ratios? Well, we're going from nitrogen, which has a molar ratio of 1, to ammonia, which has a molar ratio of 2. So it's moles of NH3, moles of N2. And now, let's see, we don't want to go to grams, we want to go to liters, because it tells us we have 15.5 liters of nitrogen gas. So, reacting to make 30 liters of ammonia. So we want to figure out how many liters of ammonia we have. So 1 mole of NH3 gas gives us 22.4 liters of NH3. So now if I do the math, what I come up with is 31.0 liters of NH3. Well, this is a great reaction because we were expecting to come up with 31, and we came up with 30. So we had a really good relationship here, really good ratio here. 30 divided by 31, our actual divided by our expected. We multiply by 100%, and we come up with a total of 97% yield, which is an absolutely fabulous yield when you're in the lab. Okay, this is the last one we're going to do on this page. So what is the percent yield of oxygen gas if 54 liters of oxygen can be obtained? Notice oxygen is going to be a product from the thermal decomposition of potassium chlorate. Oh, we just had this, didn't we? This is potassium chlorate becoming potassium chloride and oxygen. And we remembered that we had to put a 3 in front of the oxygen because we have a 3 over here. So we have a total of 6 oxygens, and now we have 2 KCl, so we're good. All right, we are at 54 liters of oxygen, so we're producing 54 liters, and we started with 500 grams. Oh, yuck, I have to figure out grams, don't I? Okay, so what's KClO3? Well, if I do the math and I figure out for KClO3, the mass of KClO3 per mole is 122.548 grams per mole. All right, let's go ahead and do the math then. We start with 500 grams of KClO3. We have to get rid of grams of KClO3. We have to go to moles of KClO3. And then we have to go from moles of KClO3 to our target destination. Our target destination is oxygen. So we have to go to moles of oxygen. And then we have to say that moles of oxygen we have to go to, well, we have to decide what units we're going to. And because they told us liters, that's what we're going to go to. So we're going to go from moles of oxygen to liters of oxygen. All right, well, let's see what we know. We know that 1 mole of KClO3 has a mass of 122.548 grams per mole. And we know that 2 moles of KClO3 give us 3 moles of oxygen. And 1 mole of oxygen takes up 22.4 liters. Okay, so if I multiply by everything on the top, divide by everything on the bottom, what I will find is that I get 137 liters. So, now, that's what we expected to get, right? 137 liters. But how much did we get? We only got 54. Well, this is a real lousy ratio because 54 divided by 137 times 100% only gives us a percent yield of 39%, which is really, really, really bad. Okay, but that sometimes happens. Anyway, that's it for the first 4 problems on worksheet number 2. Go take a break, get a glass of water, come back, and we'll do the next ones.